Okay, students. So after discussing the concept of Hurwitz polynomial, now we will discuss the concept of positive real function. Okay. So a positive real function or any function is said to be positive real function when the following conditions are satisfied. Okay, so we have a function fs which is equal to as divided by bs, and we have expressed our as in the form of s, and the powers of s are continuously decreasing. Similarly, we have expressed the polynomial bs, and we have defined our rational function fs earlier also in the same fashion. Fine. So what are the conditions for a positive real function? We will call it as a positive real function if and only if. I double f means if and only if fs is real. For s real, another thing is bs is Hurwitz polynomial, so this bs must be Hurwitz polynomial. So try to understand this. Unless you had known about Hurwitz polynomial, you could not have understood positive real function. That was the reason that we discussed Hurwitz polynomial in detail. And your third condition is that in case your positive real function, that is fs, has poles on j omega axis, means we have imaginary poles, then the poles must be simple. I talked about this when we discussed pole zero plot also. And another important thing is that their residues, I'll tell you what is the meaning of residues. They must be real and positive. With the help of one example, I'll explain that how to obtain residues under this condition. And the last condition is that we'll have to obtain fj omega. Like if you have fs available with you, you substitute s equal to j omega, you solve for as and bs. Okay, and then whatever you get, that value, the real part of that, it must be greater than equal to 0 for all values of omega. So if these conditions are satisfied, we will call our function as positive real function. I hope this thing is clear to everybody. Now, let us move forward. So, what we have to do? We have to first know about the properties of PR function. So, though we have talked about a few things in the previous slide also, first property is that we will call a function as PR, or a function is, if a given function is positive real function, then both as and bs are Hurwitz polynomial there. Then the highest and the lowest power of as and bs, they differ by unity. Okay, then if your given fs is a PR function, then reciprocal is also a PR function. That is another property. And the last property is that if you have two PR functions, the sum of those PR function will also be a PR function. So if you are already aware that a given function is a PR function, then these properties are deemed to be satisfied. So that's all you have to basically memorize. Next is testing. And this is important part. The way we tested for Hurwitz polynomial, in the same fashion we will also test for positive real function. So here also we have two kind of conditions. One is necessary but not sufficient condition, and second is your necessary and sufficient conditions. Fine. So let us see to that. uh, so your necessary but not sufficient condition, the first condition is that all the coefficients must be real and positive of the polynomial. We already know that. Second condition is your imaginary axis poles. Okay, that is s equal to j omega, and zeros, imaginary axis 0, they must be simple, means those roots must not be repeated. I told you this thing when we discussed pole zero plot. Another thing is the degree of numerator and denominator, they must differ at the most by unity. Okay, then the terms in the lowest degree also, that also must differ at the maximum by unity. Okay, and another thing we have again and again talked about, that there should not be any missing term. If some term is missing, then either all the even terms should be missing or all the odd terms should be missing. Fine. So now we need to look into necessary and sufficient condition. So if these conditions are satisfied, then we can for guaranteed uh, you can say that your given function is a PR function. Fine. So what are those necessary and sufficient condition? So first condition is they must have simple poles on j omega axis, okay, with real and positive residues. This we will discuss with the help of one example. Another thing is that sufficient condition is if fs is equal to ps by qs, then ps plus qs that must also be Hurwitz. And the third, in fact the most important one, all other conditions they are more or less satisfied when we solve for numerical. Mainly we have to check for this condition. So if fs is equal to ps by qs, then we will check for the positive realness, and this is what we have to check. We talked about this thing in the previous slide also, that real part of f j omega that must be greater than equal to 0 for all omega. So these three conditions, they are necessary and sufficient conditions for your positive real function to be the real positive real function. Fine. So now we will try to understand this PR function concept with the help of 2-3 numericals. I have purposely taken one simple numerical, one mediocre complexity numerical, and third one is your which will clarify your concept further. So in each of the numericals we have a separate concept that will be clear. So if you look at the necessary and sufficient condition, first thing that we have to do, if you look at the steps, we will determine the poles and zeros which are present in that PR function. And then we will say whether poles are on j omega axis, if they are simple or not, if they have located in positive half s plane or negative half s plane. Such kind of thing we will do with the uh, function given us for testing related to PR. So let us take one example. So here we have taken one very simple example, that is your fs is equal to s plus 2 divided by s plus 1. Okay. So we have to check this function for its positive realness. We have to check whether the function is a PR function or not. So let us see. First we'll have to see if s is real, then fs must be real. So you can see if your s is real, you put some real value for s, so obviously fs will be real. First condition is satisfied. Second is we'll have to determine the poles and zeros. Your 0 is -2, okay, that lies in the negative half s plane. Your pole is also -1, that is also lies in the negative half s plane. There is no imaginary axis pole. Okay. So we can say that second condition is also satisfied. So you see here we have pole at -1 and we have 0 at -2, and there is no pole or 0 on j omega axis. Okay. So if these conditions are satisfied, we can directly say that our polynomial is Hurwitz polynomial. Fine. So then the third condition that we talked about, we have to determine real of fj omega. Okay. So what will be fj omega? You put s equal to j omega, we get j omega plus 2, j omega minus 2. You have to solve this. You have to separate this thing into real and imaginary. So you do the cross rational function multiplication. So your denominator is j omega plus 1. You multiply with 1 minus j omega, 1 minus j omega in numerator and denominator. You get this. Okay. And you separate out real part. So real part will have this omega square, then this plus 2 divided by omega square plus 1. This is the real part. And if you see here that uh, for all values of omega, this omega square plus 2 by omega square plus 1 is going to be greater than equal to 0. So all the three conditions are satisfied. So we can say that this given function is a PR function. I hope everybody has understood this. So after we have discussed this numerical, let us move to some more numericals. that will further clarify the concept. This is another numerical where we have been given some ys, okay, which is equal to s square plus 2s plus 20 divided by s plus 10. So as I told you, our job will be first to determine uh, whether fs will be real or not for s is real. So you can see here that if you substitute s a real value, so your ys will also be real. So this first condition is satisfied, that ys will be real for s real. Second thing is, we'll have to determine poles and zeros. So what is the value of pole? That is minus 10. Okay, and if you solve the roots of this, you can very easily see that since all the coefficients are positive, so the zeros, they will also lie in the left half of the s plane. Okay, so it means the first two conditions are satisfied. Now the third condition that we have to solve is, we have to obtain the real part of f j omega. So you put s equal to j omega, so you get j omega square plus twice of j omega plus 20 divided by j omega plus 10, and you solve this and separate out real and imaginary part. Multiply this entire thing by 10 minus j omega in the numerator and denominator. You solve this, and what do you get? You get this one. And if you look at this thing carefully, you have minus of 8 omega square plus 200 divided by omega square plus 100. And see, can you say here that for all values of omega, this will give you positive values? No. Okay, so for some values of omega, it will give you positive values, the terms for which this minus 8 omega square will be less than 200. But for some values of omega, it will also give you negative values. Say, for example, say omega is 10. If your omega is 10, what you will have? 10 square, that is 100. 100 into 8, 800. So minus 800, okay, fine, plus 200. So you can see that what has happened here, you have got minus 600 in the numerator. So this is not greater than 0. So that's why this function is not a positive real function, not a positive real function. This was another example that I wanted to discuss, where we have a function which does not satisfy positive realness condition. I hope this thing is clear. Next. So this is the last example of positive realness of the function we have to check. So we have 2s square plus 2s plus 1 in the denominator, s cube plus 2s square plus s plus 2. Okay, we can see that all the coefficients are present in the numerator as well as in the denominator. There is no negative coefficient present in numerator and denominator. Okay, hence we can say that uh, your first condition is satisfied. So in the second condition, we have to determine the roots. So obviously, let us factorize the denominator part. So that factorization has been done here. You can see that those factors are s square plus 1, s plus 2. So what are the poles? That is minus 2. Okay. And another pole is plus minus j. So you can see here that in this condition, we have pole on imaginary axis. Okay, so in case we have poles on imaginary axis, the first condition was that they must be simple, and these poles are simple. Why simple? Because we do not have any power of s square plus 1. We have only two poles which are complex conjugate. There is no repeated imaginary axis poles. So that way this condition is satisfied. And another condition was that though the poles are simple and not repeated, we have to see whether their residues are real and positive. So how to find residues? So those residues are obtained here towards right hand side of your slide. So what we will do, we will solve our given ZS for partial fraction the way we did in inverse Laplace transform. Okay, and then those coefficients or factors of partial fraction, they will be called as residues. So you can see here we have split our ZS into partial fraction. where we have as by s square plus 1 plus b upon s plus 2. This is partial fraction approach. Okay, and a and b, they are called residues. So this method of partial fraction we have already discussed in detail in inverse Laplace transform. And if you obtain a, the value has been obtained as 1, and the value of b is also 1, means the residues are positive and real. So in the second conditions, one thing was your imaginary axis poles, they must be simple. If they are simple, then further condition is that the residues should be positive and real. So in this way, your second condition is completely satisfied. Now what is the third condition? Third condition is real part of zj omega should be greater than equal to 0. This you already know. You substitute s equal to j omega here. Okay, you separate out the real part, and you have to check whether that zj omega gives you greater than equal to 0 for all omega. So though I have not shown you the calculation here, you can do that calculation at your home, but I'm telling you that if you do that, it will give us zj omega, in fact real part of zj omega greater than equal to 0 for all omega. So that condition will also be satisfied, and then we can say that this given function is a positive real function. I hope these steps are clear to you. The first step is we will check the polynomials in numerator and denominator. They have positive coefficients or not. They have some missing terms or not. If we do that, we move to second part. We will determine the poles and zeros on imaginary axis. If there are poles and zeros on imaginary axis, then we will see whether they are simple or not. If they are simple, we will find out the residues. If we will check the residues are positive and real or not. If residues are positive and real, then we'll move to third condition and determine the real part of that given function for s equal to j omega, and the real part must be greater than equal to 0 for all values of omega. Then we will say that the given function is a positive real function. Okay, so that was all about positive real function, dear students. And we will stop here, and we will continue with our network synthesis in the next class. Okay.